All right, so I want to make a little video help going over the end of this worksheet. First off, on number 15, it says the law of conservation of energy tells us a couple things. One is that energy cannot be created or destroyed. But it can, I guess, comma, but it can change forms. All right, so this means that the amount of energy that was there at the beginning of the universe is the amount of energy that's there now, although it's in different forms. All right, the law, good, so that's 15. 16, a 10-kilogram rock is dropped from a height of 15 meters. So with these conservation of energy problems like 16, it's always best to start with a drawing. So I'm going to work down here because I need a little more room. And for 16, it says we have a 10-kilogram rock, so I'm just going to go ahead and draw that. It was dropped from some height here. So let's go ahead and label that, and we'll have the ground be right here. It is dropped, so its initial velocity is going to be 0. And we want to know what its final velocity is. Now this is right before it hits the ground. Obviously you're like, oh, it fell, it hit the ground. Well, it's 0. No. This is right before it hits the ground, so it's going to have some final velocity, and it's going to point in the negative direction, right? Because or whatever down is, and most likely down is negative. All right, so let's go back up and get the height here. The height says it's 15 meters, and we want to know what is this VF, or how fast it's moving right before it hits the ground. Our variable for height is going to be h. This is energy of conservation, so we'll start off by writing energy initial is equal to energy final. Then we'll think about, well, what types of energy do we have initially? So initially, right, the energy initial will be here, will be right up here. Sorry if that doesn't look great. Let me see if I can. Okay. So what I'm saying is, when for the initial part of this rock, that there's going to be types of energy would be potential, kinetic, potential of gravity, potential of a spring, potential electrics, things like that. So we can say that the rock has position in a gravitational field, meaning it's going to fall, but it has positional energy, and we know that it's going to fall. So it has PE gravitational. It does not have kinetic energy because it's not moving. There's no springs, so no spring energy, and no electric energy because there's no electric field here. All right, so once again, types of energy initial are just going to be PE grav, and the KE is 0. So I'm going to go ahead and write just PE. I could use the symbol U as well, if you prefer that. Gravitational, and no kinetic energy. If you want to write it in, I guess you could, but it would be 0. All right, so just that. Now, finally, and maybe I will write it just because, just so you can see it there and realize that it's 0 because it's not moving, right? Whereas on the other side, right, the final side, we see the opposite happening, right, with our KE and our PE grav, meaning that now it is moving, but it doesn't, it doesn't have a height. So this is going to be 0 because there's no height. You might say, well, there's a little bit of a height because it hasn't hit the ground yet. Yeah, but it's pretty much close to 0, right? It's like taking the limit as the height approaches 0. So it's pretty much, 0. All right, so there we have it, right? And we're left with just this formula right here, which is PE grav is equal to KE. Let's go ahead and fill in our formulas. Gravitational being mg height initial, because this is technically PE gravity initial, and this is technically KE final. Okay, and then over here we have 1/2 mv f, right? It's our final velocity squared, and only the final velocity is squared, not the mass or the 1/2. Okay, so looking at this, we can see something really nice here, and that is that the masses can cancel away because we have a mass on each side. So that's just us dividing each side by m, right? And we can do that and cancel the m's there, and it's all good. So I'm going to go ahead and rewrite g times h initial is equal to 1/2 VF squared. All right, so now I got to solve for VF and get my variables alone, then I can plug numbers in, or you can just plug numbers in right now, and either way is fine. I'm going to go ahead and start by just moving things around, multiply both sides by 2 just to get VF alone. Cancel that 1/2 over there because 2/2 is just a 1, so I have a 1 over there, and that's excellent. So I'm going to go ahead and rewrite now 2GH initial is equal to VF squared. And then finally, I'm going to go ahead and take the square root to get rid of that VF squared. And we're going to end up with just VF alone, right, is equal to the square root of 2GH initial. Good. All right, so let's go ahead and now we can plug numbers in. And something to remember here is that we know we're going to get a negative answer. And when we do a square root, right, if you take, say, the square root of 4, this is like saying what number squared is equal to 4, right? So the answer would be 2. But we also know that negative 2 squared is also equal to 4, right? So what I'm trying to say then is when you square root 4, that you get you can actually get 2 answers from it, the positive or the negative answer of 2, positive or negative 2. So coming back here, we can see that we're going to get 2 answers, but only one of them is going to make sense, and we're going to throw the other one out. So the one that's going to make sense is that the rock is moving downwards and that the velocity final should be negative, and the positive answer we're going to throw away here. All right, so let's come back down here. Let's go ahead and plug in our variables we know. So VF is equal to the square root of 2 times 9.81 meters per second squared times 15 meters, which is our height. We can notice that the units are going to be meters times meters. Well, let's get a number first, then I'll point that out. 2 times 9.81 is 19.62. We'll multiply that by 15. We end up getting 294, and you should always type that in, 2 as well, just to be sure. 294.3 units are going to be meters squared over seconds squared. And so when we square root meters squared per second squared, we end up getting meters per second, and square rooting 294.3. Let's see what that is. Square root the answer. Whoops, end parenthesis. It's going to be 17.155. So I'm going to go with 17.16 if I round meters per second. And this is my final velocity of the rock in the negative direction, right? So I'll add that negative sign there, or you can say downward, and that works too. Because velocity is a vector, it has both magnitude and direction. So you could write that little vector hat over it if you want, but there is a negative sign there, or you can say downward. All right, good. Let's go to the next one. It says 17, a 10 gram bullet is shot into the air at 400 meters per second. How high will it be when it stops? Okay, so on 17, I'm going to go ahead and start here with a drawing, right? Always, I think drawings just help. So there is a bullet which is going to be fired upwards, and the bullet has a mass of 10 grams. Now, right away, that should be an alarm bell because we like kilograms. So let's remember here, grams is we'll put it right here. Put the star right here. So we have grams, and we have to get to kilograms. This is hecta, this is deca. And so we can see here our decimal has to go 1, 2, 3 to the left. So right here, as I put the decimal next to the 10, I'm going to go 1, 2, 3 to the left. Anywhere I have an open valley gets a 0. So we're saying 0.01 kilograms. All right, good. So we fixed that right away, and that's good to know. All right, so and it's fired upwards. I believe the velocity they told us was, this will be our initial velocity, is 400 meters per second, and it's going to be in the positive direction. It's going to be upwards. And we want to know what height it gets to at the end, right? So we want to know what HF is. All right, and I think I got that right. I should probably double check just to be sure. Yep. How high will it be when it stops? So when it stops, so when the bullet gets to right here, we know that its final velocity, if it stopped, is 0. All right, so this is pretty straightforward. It's kind of a reverse of the last problem in a way, right? So I'm going to start here by writing my energy initial is equal to energy final. I see that initially, the two types of energy we were talking about were KE initial and PE initial. But we can see here that initially we don't have any height. So, so our PE initial is 0. All right, and then on the final side, we can see that we have KE final plus PE final. But here we can see that on the final side, we don't have any moving energy because it gets to the top and it stops. So it looks like this for our conservation of energy. Let's go ahead and rewrite that and make it look a little bit better. KE initial equals PE. And this is gravity. I got to be a little more careful there. Final, because we know there's other types of PE. All right, so we get something like this. We'll go ahead and write our formula. 1/2 MVI this time squared is equal to MGH final. All right, and once again, we notice that we can cancel something off here, and that would be the mass. So, all right, we can rewrite again. So we have 1/2 VI squared. I think we're in the same place we were last time pretty much with this equality. Slightly different, but pretty much the same. But this time we're not solving for VI, we're going to solve for H. And so we can just do one move here, I think, to get this to look the way we want. And let's just kick the G over to the other side, right? So I'm going to go ahead and do that, cancel the G right here, and I end up with H final alone on that side, which is what I want, is equal to 1/2 times G times VI squared. And if you want to be particular here, right, that you can rewrite it one more time as G VI squared over 2, right? And that's because that's the same. That's the same as what we just had up above with that half. I just thought I'd do that just to show you that. All right, so I'm going to go ahead and plug in my variables I know. So I know G is 9.81. I know the initial velocity is 400 meters per second upwards. Divide that by 2, set it equal to HF. It's a job for our calculator. Top of the fraction is 3,924. We're going to divide that by 2. And, what would that be? I'm trying to do that in my head. 1962. And units here, I should be careful. I need my units. Should be meters. All right, and there it is. Okay. So, we finally have a pendulum problem. All right, so it says a pendulum is 0.8 meters above its lowest point when it is pulled back and released. Okay, how fast will it be moving at its lowest point if it has a mass of 8 kilograms? All right, let's look at this. So I believe we have something like this. This is problem 18, and we have a pendulum. And a pendulum is a mass on the end of a string, and it is going to move, is going to oscillate back and forth between these 3 points right here. And so what I'm trying to say or trying to draw here is that this pendulum is going to swing back and forth like this, right? And that should be pretty straightforward. I think we've seen a pendulum before, but that's the basic idea. Something to keep in mind is that this height here, or this distance, is going to be the same as this over here, assuming no energy is lost or dissipated, because we will lose energy, right? Over time, this pendulum will stop swinging back and forth. But for right now, we can assume that these heights are the same and we're not losing any energy. If we think about this, this is interesting. We can call the ground zero, but I think it's actually easier to call this line right here zero. So we'll say that there's zero PE. So we'll say PE grav is equal to 0 at that red line. And what this is going to allow us to do is realize that when we're at this red line, that all of our energy is going to be KE. And so I'm saying this will equal the total energy right there at the bottom. Now, when the pendulum swings up to here, it is going to have a height above the red dotted line, and therefore it is going to have potential energy gravitational is going to equal the, actually it's going to equal all of the energy because it stops moving right here. Right here, the pendulum is stopped. And how do I know that, right? Because it seems like it just is moving along, swinging back and forth. Well, it has to change directions. And if it has to change directions, it has to stop. So that's how I know that. And if it's stopped, then we know at that very moment, that split second, that KE is equal to 0. All right. And then the same thing is true over here, that it's stopped as well. And therefore, the KE is 0. And the PE gravitational is equal to E total. So what we have here is an object oscillating back and forth, changing energy from kinetic to potential. And if it's not losing any due to friction or air resistance, which it is, but if we pretend it's not, then it's just transitioning, and this energy is just changing back and forth between PE and KE. And then obviously if there was a point maybe here in blue, right, in between right here, then there at this point there would be some combination, right? There would be it would have both PE grav and it would have KE, but neither would be at a maximum, right? These two together would equal the total energy. All right. So this question is going to be a little simpler and ask us just about one of the maximums and minimums here. So it says for question 19, a pendulum is 0.8 meters above its lowest point when it's pulled back and released. How fast will it be moving at its lowest point if it has a mass of 8 kilograms? All right, so we're saying now that this height is 0.8 meters, and we are saying that the mass is 8 kilograms. Okay, so if that's the case, then and we know that we're starting right here, right, with the pendulum being whoops, let me undo that. Okay, just trying to get the highlighter. We are starting at this point right here, right, in yellow. And then our final point, which is we want to know how fast is it moving at the bottom. So we want to know about this point right here. So we want to know what is the final velocity, what is VF right here at this point. is the idea. Okay, so let's go ahead and let me just double check that really quick. Yep, okay. So let's go ahead and solve this. So we have our initial point, which once again is right here at the top. So we're going to say energy initial is equal to energy final, which will be at the bottom. And we know at the top we have all PE, gravitational. I'm going to use the other symbol this time. There's no kinetic energy because it's not moving at the top, and I'll keep the I in there. And then at the final, we know it's just moving energy, so it's all KE, and I'll keep the F in there. So KE final has no potential energy because it's at this dotted line, right? It's at this 0 line right here. All right, good. So let's go ahead and use our formulas. So we have MGHI is equal to 1/2 mVF squared. And we can go ahead and cancel away the m's. That's very nice. And this is a lot like, I think, the first problem we did. We'll multiply both sides by 2, right? Kick that 1/2 out of there and get VF alone, right? We want VF alone so we can solve for it. So we end up getting this, cancel the half with the 2. 2/2 is a whole, is 1. So, and then we can just square root. So we end up with VF equal to the square root of 2GHI. I forgot to draw that square root in. There you go, something like that. And this time, will the velocity be negative? Well, it's going to be pointed to the right as I drew it out up above, right? As it swings back here, it's going back in the other direction. So I guess it would be a positive velocity. Not so much worried about it with a pendulum problem, but it could just equally apply to a pendulum problem. If it was moving to the left, it would be negative. All right. So anyways, let's plug in what we know here. So we can say VF is equal to the square root of 2 times 9.81. Our height was just that's a squared, is just a 0.8 meters. So let's go ahead and plug that in the calculator really quick here. 2 times 9.81 times 0.8 is 15.696. Always try and round at the end, so I'm going to square root that. Square root, second answer, end parentheses equal to 3.961. So I'm just going to go 3.96 meters per second. This was units here, it was meters squared per second squared. All right. And, velocity usually has a direction, so I'm going to go ahead and say right. But, you could have drawn that problem the opposite and said it was moving back the other way. So whatever. All right. Anyways, I'll leave number 19 for you. Hopefully that's making more sense. Go back and watch the video if it's not. And I think 19, how fast is the pendulum? Oh, okay, so that's actually an interesting, or 20. I'm going to leave 20 for you. I did 19. 20 is interesting because it asks about a point halfway, right? So there's actually a couple ways to do that. There's an easy way where if it asks about, it says, how fast will the pendulum in question 19 be moving when it's 0.4 above its lowest point? Well, you could just take its total energy at 0.8, which is all potential, and divide by 2. All right, but that's kind of a cop-out, right? I think it's, it's a good way to do it, but a nicer way to do it, right, is to say this. If we're looking at the pendulum being here to now just being at some intermediate point, right? It's like the blue point that I drew down here or up here, wherever the heck I drew it. Let's see. So it's like this point being 0.4. This is what I'm asking about. So what I think is cool here is you can have your initial type of energy be all PE, grav, and your final type of energy be PE grav plus KE. So if I was setting up the energy conservation for 20 and wanted to do it in a way that was a little more challenging, I would set it up like this, right? I would go PE, or I would say, actually, EI equals EF, right? I'm going a little fast. I would then say PE gravity initial is equal to KE final plus PE grav final. And then I would say we would have here MGH initial is equal to 1/2 MVF squared plus, and this is like, you might say, well, it's not the true VF. VF can be wherever we want it to be, right? It doesn't have to be the final location. It's just, final just is relative, right? We're calling this final. And this is going to be, whoops, I have another equal sign in there. That should be a plus sign. Plus MGHF. So what I want to point out here is this H is going to equal 0.8 meters. This H over here is going to equal 0.4 meters. And notice one more thing. This is really cool. Check this out. Right? You can cancel all of those, and the plus sign doesn't matter so much because each term has an M in it. And then that's why it doesn't matter. Because, you know, sometimes with those plus signs, you got to watch out because it's not always easy to factor them. And it can be a little tricky if one of the terms doesn't have an M, but all of these have M's. So anyways, I will let you finish that, right? And figure that out. Hopefully this is making sense and everybody can have a good day. And so you can't cancel the G's out. That's what I'm trying to say, right? You cancel the M's out because each one had an M, but now each one doesn't have a G, and you can't cancel that out. So go ahead and find that velocity and have a good day.